Hello, in this film we're going to look at the Nobel Prize in Physiology or Medicine from 1911, awarded to Allvar Gullstrand for his work on the dioptrics of the eye. And this is a lecture summarized by me, how I found the mechanism of intracapsular accommodation. Here you see, pardon, by the way, a slit lamp, a device he worked on, and I think he even invented the version of it. And the same is true for the otoscope, also a device used for watching eyes and ears. And the ophthalmoscope, that is what he worked on. Sorry, the left one. Then is Nobel Prize lecture with the name How I Found the Mechanism of Intercapsular Accumulation. Hadden we already seen. Summarized by me, here we go. The normal eye can see clearly at different distances. Therefore, the lens alters its shape. That is called accommodation process. The lens is enclosed in a capsule. The extracapsular accommodation mechanism has been studied. What is happening inside the capsule is the subject of this lecture. The lens consists of an infinite number of fine fibers which terminate at different depths inside the lens, running from one end to the other in coils. The fluid inside the lens clearly lacks elasticity. The fiber itself must retain a constant volume. A change in the shape of the fiber results in a change in the shape of the coils. The lens is clearly no ordinary homogeneous medium. In the young, its refractive index is varying. The laws governing optical image formation in such medium were unknown, and what was known was wrong. Most people think that optical image formation is focusing on light rays coming from one point of the object to one point in the image. This idea of image formation does not apply to the eye. I must agree with that. I have also learned that in school, but here it says that it is wrong. Point-by-point image formation happens only at the central axis more or less, but not outside that axis. If you use an ordinary biconvex lens in the object of a camera, a tolerable image is found where the optical axis intersects the plate, but if we magnify, we found that the point is not really projected as a point. With a small aperture, the point-by-point theory works reasonably well. A straight line in the object is projected as a straight line. That means the projection is collinear. But the actual circumstances of optical image formation, if we have a large aperture and a large image field, the law of collinear projection does not apply at all. Allvar was one of the first to see this. Modern photographic objectives, however, come close. How is an image built up after refraction? The normal case is that the projection is astigmatic due to rotational asymmetry, which is not the exception. It means that there is not one focal point, but there are two. As more as anastigmatic bundles can be considered homocentric, the smaller the iris aperture is relative to the focal point from the iris. The so-called Sturm conoid was discovered and forgotten. In the case of eyes, the aperture is larger than the focal range. Gullstrand underlines that the Sturm conoid was derived mathematically, but differential quotients higher than the seconds were ignored. Gullstrand set himself to the task of taking into account differential quotients of the third order in the balanced plane equation, and he found also doing experiments results concerning the structure of astigmatic rays sufficient for practical purposes. Laws governing the occurrence, but not the essential. And that on a point for a monochromatic ray in the paradoxal region coming from an infinite point, the simplest case is possible. He also criticized others treating optics as two-dimensional while it is three-dimensional. In reality, the light makes an angle with the central axis. Such a light bundle is astigmatic, with finite asymmetry values. But how the bundle is refracted in the eye is still unclear, since the accommodation mechanism is still unknown. Physiological optics deals with rays along the centric axis. Deviations in the focusing is known as spherical aberration. The aberration depends on the shape of the surfaces. Helmholtz already subsisted the term with monochromatic. A more general theory for other cases was still needed, thus all the different quotients above the third had to be taken up. I was not able in my early works to do is give a complete study of the anesthetic rare bundles and the geographical significance of the asymmetry values. The mathematics needed is the hardly investigated lines of principal curvature of single points and the relation between the two caustic surfaces at common points of contact. This is part of the discipline of torrential geometry, which studies smooth shapes and surfaces. That's a remark by me. Only later I was able to do such an investigation needed for the dioptrics in general and the dioptric of the eye, converting anesthetic ray bundles with a focal range small in comparison to the aperture. Here we see the two of the illustrations. Here it comes. The method I developed shows aberration in the ray refracted in the rays are complex and that the radiant emissions seen around lights in pints, star shapes, expresses the individual character of the aberration. See figure 1, here you see it. Yeah, the star shape. Investigations show me that the light distribution inside the ray bundle is more important than the size of the cross-section of the bundle in relation to achieving a sharp picture. The light intensity is greatest when rays of light converge. The points they converge are located on a caustic surface. These surfaces are central in image formation. And then remark by me, a caustic surface is the boundary separating accessible and inaccessible regions for a given family of light rays. The study of the effects of diagrams was also needed, thus because the diaphragm also works like a lens. As seen earlier, a point is in general not reformed as a point on the screen. Ebbe knew this, but how I overcame this problem, he could not explain in a satisfactory way. Gullstrand repeats the general following from this basis equation. Point-by-point imaging does not take place, only more or less in the center. After studying optical image formation in general, the next step was to study heterogeneous media, in particular the eye lens. The refractive index in the eye lens varies from point to point. Light inside does not travel along a straight but in a curvilinear path. The same is the case in the Earth's atmosphere, also a non-homogeneous medium. I showed that the mathematics applied for the image formation in the case of homogeneous media also applies to heterogeneous media. It also applies when light travels between one medium and another, homo or heterogeneous. I now was able to understand the extracapsular accommodation mechanism in the eye. Accurate knowledge was needed of the surface and the thickness of the cornea. These were not correctly measured since the refraction by the cornea was seen as none. To calculate the refraction, I used equations established by Mathison. But he only took account of the first and second order differential equations to calculate the refraction index. It was sufficient. It leads to a formula for the total index of the lens, which was invariance with facts. So the differential quotients had to be taken into account to the fourth order. As a result, 7 constants had to be found. 6 could be arrived, and a 7 by using certain acceptable assumptions. This was done for the lens in rest. Next task was for an accommodated lens. For that measurement on the change in curvature of the lens had to be made, mainly for the anterior surface. The posterior surface hardly changes shape. I added 2 conditions. The center does not compress. The largest enclosed isoindixial surface does not change in volumes. See figures 3 and 4 for a lens at rest and a maximum accommodation. The refraction index at the poles is 8.386 and 1.406 at the center. The index rises from the surface to the center, first fast, later slower. The lines in the figures are also isoindicial, that means they have the same refraction index, also remarked by me. Let's go to the 2 figures. Here you see the shapes he describes in the text. Yep. Yeah, okay, so let's read again. I added 2 conditions. The center does not complex. The large enclosed isoindicial surface does not change in volume. See figures 2 and 3. Okay, the shape of the isoindicial surface are calculated correctly. Maybe there's a slight asymmetry, but it won't change too much. In general, they have the shape of parabola, except at the edges. There are still things unknown about the actual shape of the lens. Measurements are needed. Clear change in the figure is larger than expected coming from the shape change if the lens would be homogeneous. This is remarkable. It follows from figures 2 and 3 that within the closed isoinitial surface the contraction in the equatorial plane is largest close to the axis. Contraction, in the equatorial plane is largest closest to the axis, but there is also horizontal contraction. During the accommodation, the tension of the zone null reduces as Hesmel suggests. This view was attacked, but has proved it. During the accommodation, the volume inside an isoinitial surface remains the same, but its area increases. A sphere has a smallest area for any volume. The star shape one sees when looking at the luminous point are caused by the shape of the lens, more precisely by the shape of the isoinitial surface, shallow, radial and folded. Gullstrand was able to prove this mathematically. How does the lens contract? It consists of fibers in a loop shaped, the loop aligning to the equator. They are packed very tightly, with them take a hexagonal shape. Gullstrand describes how and how much the loop contracts at different places in the eye. At the same places, the loop must even the loop must even stretch to allow the lens to take form. The calculations agree with the observation. It should have been impossible to foresee that the total index of the lens increases during accommodation, and Helmond's accommodation theory was correct. Even experiments contradicted it. Was of course in Helmond's time. In Gullstrand's time, the experiments confirmed it. Well, this is not an easy subject. I've read somewhere that even most of his direct colleagues had difficulty to understand it because of the advanced mathematics he used. And in his lecture he does not, but if you read his articles and his books, then you will see a lot of mathematical formula and differential equations and more of that. It's not easy stuff. I've tried to summarize it as best as I could. Here you see some pictures from the fibers in the lens, coming from Wikipedia, as you can see. These are lens fibers, and these straight fibers, as you can see. And this is a picture of it schematizes how the fibers are in the lens, as you can see. This is of course curved. Okay, this was it. Thank you for watching. Next week we will go to the Nobel Prize in Physiology or Medicine for the year 1912 with general information about the work and some biographical information and an awards ceremony speech. And the week after that we will see the Nobel Prize lecture summarized in another movie. And thank you for watching, and maybe till another time.